Hey class, this is Dr. Martino. I hope everybody's doing well. Hey class, this is Dr. Martino. So this is a short little video I'm hoping that will focus on length tension relationships in skeletal muscle. And these relationships also apply to cardiac muscle. So I'm only going to have 2 slides, hopefully no longer than 7 minutes on this thing. So what you're seeing here is on the y-axis you have a percent maximum isometric tetanic contraction, right? So an isometric contraction is where you have cross bridges formed, but there's no shortening of the sarcomeres, okay? So imagine that you lock your hands underneath a heavy desk so that your forearm and your humerus are at 90 degrees, and you try to barbell curl that desk, which you can't do, right? You're still applying a force. You still have cross bridges that have formed, but you don't have any shortening, okay? On the x-axis here, you have the percentage of length of an individual sarcomere. So this graph only represents one sarcomere, not an entire muscle. 100% is normal resting length. Most skeletal muscles rest at 100% of their length. Okay, so the resting length is 100% of the length, and the optimal length is 100%. Okay, that becomes very, very important when we get to cardiac muscle because resting and optimal length are not the same. Okay, so the heart is wired a little bit differently. Okay, so what you have here is you see that you're going to get between roughly 90 and about 110% of length. You're going to have resting length of the muscle. All right, and so most people sit between this range, and that's going to be the optimal beginning point to start a contraction so that you can get maximal overlap ultimately of actin and myosin. All right, so what do we see here? It's an inverted U shape on this graph. Remember, this only represents one sarcomere, which is the functional unit. If you move down to about 80% of resting length, right, what happens to the force? Well, you started here from about 90%, give or take, right, and you're at 100% of force production. If you move to 80% of length, right, so you shorten the muscle by 10%, you flex the bicep by 10%. What you get is you get a decrease in the amount of force that can be produced if you start at that length. Okay, if you shorten it even more, let's say you start at about 50, well, let's see, about 70% of the resting length of the muscle. So you pre-select 70% of whatever 100% length would be, okay? And you draw a line straight across to the amount of force being produced. And you can see that it's roughly 55% of the force. So if you start isometric contractions, remember contraction where you don't move, from less than 100% of resting length. So in this case, it's the bicep that we're talking about. 100% length would be your arm at your side. As you decrease the starting length, meaning that the bicep is already more contracted when you start the contraction. I know that's kind of sounds strange, but you're starting it from a shorter length. The amount of force that you can produce is less. So if you wanted to curl the maximum amount of weight in a bicep curl, okay, you would start the bicep curl from resting length, which is your arms both at your side. If you were to start it more contracted, as you can do in some bodybuilding exercises where they start at 70% or 50%, what you'll notice immediately is that the amount of force that you can produce is a lot less. Okay, so let's go to the other side. The other side of this thing, you're going to see that as you go up in length beyond 110%, the force production goes down too. So here's the fundamental problem with the right side of this curve. In order to get to these types of lengths, you would have to physically cut the tendon of your bicep, to be able to get to these lengths. So these types of experiments were done in frogs or rats where they dissected out a muscle and were able to get these muscles to go much shorter or much longer in length. And that's how they conducted this. So this is totally artificial. The bottom line is if you want to produce the most force, you need to be starting your contraction between 90 and 110% of resting length in an isometric contraction. This is the sweet spot in the curve. I think I will end this one here, and then I'll talk about passive force, the next slide, in another video. So this is isometric contraction, and it tells you something about each individual sarcomere and where they have their maximum capability. You can see these pictures here that when you're at this point, there's too much overlap of actin and myosin, so you don't get optimal contraction. And over here, where you have an overextension, you have, again, not enough actin and myosin overlap, therefore you don't get as much force production. Here you have the sweet spot where you have maximum actin and myosin overlap, and you get maximum force production. All right, guys, that's all I got for now. Wait for the next video.